Lattice points are points whose coordinates are both integers. For example, 1, 2 or -5, -3, but not -1/2, 3/5. A lattice polygon is a shape made of straight lines whose vertices are all lattice points. Let's say that we want to calculate the area of this lattice polygon. We could do this by dividing our shape into triangles, then calculating the area of each triangle and adding them all together to get the total area. For our shape, we would need to calculate the area of 6 triangles. But what if our shape was more complex? For example, like this. The time to count all the triangles would be much longer. In 1899, Georg Alexander Pick published an article where he first stated his theorem. He provided a formula for the area of lattice polygon in terms of the number of lattice points within it and on its boundary. It was not popularized until Polish mathematician Hugo Steinhaus published it in 1969, citing Pick. The Pick's theorem goes like this. Let I be the number of integer points interior to the polygon, and let b be the number of integer points on its boundary. The area of the polygon would then be equal to b divided by 2 plus I minus 1. The area of this polygon, using this formula, would be 8 boundary points divided by 2 plus 15 interior points minus 1. So that is 18. Now let's prove this theorem. This is a 5 by 4 rectangle. It has 18 boundary points and 12 interior points. Now let's color one square for every interior point like this. We are left with 8 squares that are not filled. Let's use the boundary points to fill those squares. We used 8 boundary points out of 18, so that is a half minus 1. So the area of this rectangle is 12 interior points plus half of the boundary points minus 1. Now let's prove that this formula works for every polygon. Let's split our rectangle into 2 triangles with the same area. The rectangle has 12 interior points. Each triangle has half of that. The rectangle has 18 boundary points. Each triangle has 10, so that is a half of the rectangle's boundary points plus 1 because they share 2 boundary points. The area of the square is equal to b over 2 plus I minus 1. The area of one triangle should be equal to half of the interior points of the rectangle plus half of the rectangle's boundary points plus 1 divided by 2 minus 1. After simplifying, we get I plus b over 2 minus 1 divided by 2. And that is true because one triangle has half of the area of the rectangle, and the formula for the area of the triangle is just the formula for the rectangle's area divided by 2. So now we know that the Pick's theorem is also true for the triangles. Now let's look at 2 different polygons, a square and a rectangle. The square has 16 boundary points and 9 interior points. From the Pick's theorem, its area is equal to b divided by 2 plus I minus 1, so that is 16. The rectangle has 20 boundary points and 7 interior points, so its area is 16. When we combine the 2 shapes like this, the area of the new shape is equal to the sum of the areas of rectangle and square. We can write it like this: b1 plus b2 divided by 2 plus I1 plus I2 minus 2. The shapes are combined along the line marked yellow. This line consists of 3 points, not counting the ends. If the Pick's theorem holds for any lattice polygon, we can write the area of the combined shape as b over 2 plus I minus 1. The number of boundary points of the merged shape is equal to b1 plus b2 minus 2 times L, because the points on the yellow line are now on the interior and must be subtracted from every shape's boundary. Minus 2, because the points at the ends of the yellow line are now shared by 2 shapes. The number of interior points of the merged shape is equal to I1 plus I2 plus the number of points on the yellow line. If we plug in those values into the Pick's theorem, we get this formula. After simplifying, we can see that L's reduce, and we are left with the same formula as the sum of 2 shapes, so the Pick's theorem holds for merged shapes. With this knowledge, and the information that the formula is also true for triangles, we can conclude that the Pick's theorem works for any lattice polygon, because every lattice polygon can be divided into triangles. We can easily calculate the area of this shape knowing the Pick's theorem. It has 8 boundary points and 15 interior points. So, when we plug those values into the formula, we get 18. But what if our shape has a hole inside? Will the Pick's theorem still work? To calculate the area of the shape without the hole, we could just calculate the area of the whole shape and subtract the area of the hole. But there is an easier way to calculate the area of the shape with a hole, or even with multiple holes. Let's first look at it like there was no hole. So it has 8 boundary points and 15 interior points. Now let's look at the hole. The hole has 4 boundary points and 2 interior points. The area of the shape without the hole will be equal to b1 over 2 plus I1 minus 1. The area of the hole is equal to b2 over 2 plus I2 minus 1. If we subtract the area of the hole from the area of the whole shape, we get b1 minus b2 over 2 plus I1 minus I2, and the ones reduce. Now let's look at our shape with the hole. It has 12 boundary points and 9 interior points. Now let's write b and I using b1, b2, I1 and I2. We can see that the number of boundary points of the whole shape is equal to the number of boundary points of the shape without the hole plus the number of boundary points of the hole. The number of interior points of the whole shape is equal to the interior points of the shape without the hole, minus all the points of the hole, so minus b2 and I2. From this equation, we can see that b1 is equal to b minus b2. From the second equation, we can see that I1 is equal to I plus b2 plus I2. Now let's substitute those values into this formula. We get b minus 2b2 over 2 plus I plus b2 plus I2 minus I2. After simplifying, we are left with b over 2 plus I. This is the Pick's theorem for a shape with one hole. But what if we added more holes? Now our shape has 3 holes. The shape without the holes didn't change. It still has 8 boundary points and 15 interior points. Let's look at the first hole. It has 4 boundary points and 0 interior points. The second hole has 3 boundary points and 0 interior points. And the third hole has 4 boundary points and 1 interior point. The area of the whole shape with the holes would be equal to the area of the shape without the holes minus the area of the holes. The area of the holes is equal to the sum of the areas of each hole. So it's equal to b1 over 2 plus I1 minus 1 plus b2 over 2 plus I2 minus 1 plus b3 over 2 plus I3 minus 1. We can write it like this: b1 plus b2 plus b3 over 2 plus I1 plus I2 plus I3 minus 3. Now let's write that the sum of all boundary points is equal to bh and sum of all interior points is equal to ih. So the area of the shape with the holes is equal to the area of the shape without the holes minus the area of the holes. So that is b0 minus bh over 2 plus I0 minus ih plus 2. From the example with one hole, we know that the number of boundary points of the shape with the holes is equal to the boundary points of the shape without the holes, plus the boundary points of the holes. And the number of interior points of the whole shape is equal to the interior points of the shape without the holes minus all the points of the holes. From the first equation, we can see that the b0 is equal to b minus bh, and from the second equation, we can see that I0 equals b plus bh plus ih. Now we can substitute those values into this equation. After simplifying, we get b over 2 plus I plus 2. That is the Pick's theorem for a shape with 3 holes. Now let's compare all formulas. The Pick's theorem for a shape without any holes, with 1 hole, and with 3 holes. Let's subtract and add 1 to the second and the third formula. we didn't change the value, but now we can see that if we want to calculate the area of the shape with the holes, using the Pick's theorem, we just have to add the number of holes to the regular Pick's theorem. So, the general formula for calculating the area of any lattice polygon with any number of holes using Pick's theorem goes like this. Number of boundary points divided by 2, plus the number of interior points, minus 1, plus the number of holes.